Okay, it's 5 o'clock, so we're going to go ahead and start this Ask Me Anything. So my name is Emery Berger, I'm a professor at UMass Amherst, and it's my honor to host my friend Michelle Strout, who's a professor at the University of Arizona. So Michelle has been a professor in the Department of Computer Science at the University of Arizona since August 2015. Michelle's main research area is high performance computing. Her research interests include compilers, runtime systems, scientific computing, and software engineering. She's received a number of awards for her research, including a career award for her research in parallelization techniques for regular applications, and a DOE early career award to fund her work on separating the specification of scientific computing applications from the specification of implementation details, like how to parallelize those computations. Some of her research contributions include the universal occupancy vector for determining storage mappings for any legal schedule in a stencil computation, the Sparse Polyhedral framework for specifying inspector executor loop transformations, data flow analyses for MPI programs, parameterized and full versus partial tiling with outset and insets, and loop chaining for scheduling across stencil loops. And with that, I will start asking some questions that are coming in on Slack. And we'll just start. Sorry. So the protocol will be, I'll ask a question, then I'll shut the hell up. And then Michelle will say, okay, I'm done, or something like that, and then I'll talk again. Okay, perfect. So the first question is from Kazem Cheshmi from the University of Toronto. And he asks, he says, runtime inspectors are pretty standard in practice and are implemented in research compilers. What are the obstacles for integrating them into existing general purpose compilers like LVM or GCC?
Okay. Yeah, I think that's a great question, because in practice, what people are doing is they're writing the inspectors as part of a library. So you'll have like a sparse matrix library, and it'll have various algorithms. And then you'll have an inspector piece that will look at like, well, what's the structure of this sparse matrix so that we can figure out how to schedule it so that it has good data locality and it has good parallelism as well. And I think the issue with getting it into general purpose compilers is that the way those sparse tensors or sparse matrices are stored varies greatly. So we spend a lot of time looking at when is it stored using arrays, and you've got index arrays. And we're able to do some analysis for that. But in general, there's a lot more variety. I think there's various pointer-based data structures that are storing sparse tensors, and so doing the analysis in a general purpose compiler, even if it's done at the level of like the AST and Clang or something like that, is gonna I think that's quite a hurdle that is going to happen. And then if you think about LLVM, that's really, you've got some of the array abstraction, but it's mostly a lower level abstraction as to what's going on. And so I think that's why we're going to have more of this code generation approach to this problem.
Okay, that makes a lot of sense. Let me ask a quick follow-up. Have you heard or are familiar with the Apache TVM thing that has come out of the University of Washington? I ask because it's a tensor virtual machine thing.
Yeah, for doing TensorFlow. I have, but I haven't done any in-depth research about that. So what are they doing? Are they...
So I'm not an expert at all, but my impression or my recollection is that essentially tensors are elevated to being sort of first-class objects. So you do operations over tensors as opposed to doing operations over scalars, and then maybe with vector intrinsics is the sort of standard thing that we do in like x86.
Right, and when we have those higher level abstractions, either at the library level or with something like what you were just mentioning, that's when we can actually bring to bear some of the technology that's been developed to automatically generate some of those inspectors. So we've been working on it for a while, but the more general purpose compilers don't have the higher level abstractions that we can get our hooks into.
Okay, great. So so let's see. So there's a sort of related question. This is from Kishantan Sundaraja from Purdue. What are some of the key challenges you faced when developing the Sparse polyhedral framework? And what steps have you taken to broaden the impact of this framework?
Okay, what were some of the key challenges? Well, one interesting thing is it's kind of how the Sparse polyhedral framework came about. So when I was in grad school, I got really interested in the polyhedral framework and this whole idea of you can represent loops as this mathematical object, and then you can manipulate them by orthogonally specifying schedules and also affecting the data mapping and doing things like tiling. I mean, this was super cool in my mind. So this was like the shiny object that caught my attention in grad school and kept it. And so I got more and more involved in the polyhedral model and did some of that initial storage mapping work I actually did pretty early, like my second year of grad school. And then I realized, wow, like there's a ton of papers in this area. There's a lot of PhD theses already in this area. So how can I get out on the bleeding edge and innovate and be different? And so that was actually why I switched to the Sparse codes. And so I started looking at the Sparse codes, and then the real kicker was we were talking with a collaborator at a government lab, who I won't name. And he basically said, we were saying, okay, so we're going to be scheduling these Sparse codes in the way that you do the orthogonal scheduling with polyhedral model. And he said, oh no, you can't do that. And so that, of course, is, so then I had the challenge. So I was like, okay, I'm going to do Sparse and do the challenge. So, so that was the that was the beginnings of the Sparse polyhedral framework. And then it was really trying to take some of the work that had come out of Bill Pugh's lab, where they had looked at how can we do data dependence analysis when you have these indirect array accesses and not everything is this nice affine expression of the loop iterators, and how can we extend that to then specify schedules, et cetera. So then the other part of the question, I guess, was what have I done to try to make that work more well known? I'm not quite sure how to answer that one, but I would say that when you're doing research, making anything that you do open source and available to others, I think is important. And so we do have this IEGen, so Inspector Executor Generator library that we've had out for a while, available on GitHub, and it manipulates sets and relations that have these uninterpreted functions in the Sparse polyhedral framework. I think we're still trying to make progress on the Sparse polyhedral framework. It's not as straightforward as just the polyhedral, because you have to have some way of specifying the inspectors as well. And so, we don't have the tools are not nearly as mature as in the polyhedral community, where those tools have quite matured, and we in fact use them to help build the Sparse polyhedral framework tools as well.
Great. So, so Ali Donaldson at Imperial and Google has a question, which is kind of a follow-up. So he says, my impression as a bit of an outsider is that for some years, polyhedral techniques weren't that practical due to requiring somewhat idealized conditions to hold for the program under analysis. So I think he's not talking about Sparse here. To what extent do you think that that's changing? Could we soon have programs benefit from polyhedral compilation when we compile with just -02?
With just -02? Well, I think that many people may not realize that polyhedral transformations have actually been a part of general purpose compilers for more than a decade now. And so they are already being, some of the technology that's been developed as part of this research community has already been used to do various loop transformations, loop fusion, et cetera. And so there are definitely limitations from the standpoint of what the loop bounds need to look like and what the accesses need to look like. But I think that as we, it's the same kind of problems we run into anytime we're trying to do transformations that go over larger portions of a program. You run into needing interprocedural analysis and understanding what's pointing at what. And so as the broader compiler community is able to do those kinds of difficult program analyses in more detail and better able to handle interprocedural analysis, that has been helping the polyhedral community make more and more progress and have more of an impact. But I think what's really making these techniques come to a fore is the more prevalent use of deeply embedded domain-specific languages. And so you have more and more often things like TensorFlow, for example, where you specify a computation like an image pipeline or a neural network pipeline, a deep learning pipeline. You specify it at a higher level, and as it runs, it first creates an intermediate representation of the computation that's going to happen. And those intermediate representations often have enough information and do fit it within the polyhedral model or the Sparse polyhedral framework. And so we are able to then apply some of these scheduling technologies and code generation technologies in these settings. And so, yeah, I think it's already making an improvement, and I think we're just going to see more of it.
Yeah, I mean, I actually have, for fun, not in anger, used some of the polyhedral optimizations that were in Clang. So it's definitely, like, I didn't have to do anything particularly special to access them, but it wasn't on by -02. So if Ali is insistent that it be -02, we'll just change what -02 means. But going back to your EDSL comment, which segues perfectly into a question that has a number of thumbs up right now. So this is from Sabri Blackman at CU Boulder. So Sabri says, you've taught the only course on EDSLs I've seen in a comp sci program. How are EDSLs different from normal language construction paradigms such that this topic is rich enough to not only teach, but advocate? I'm a huge fan personally.
Well, I'm definitely not the first person to teach a class on EDSLs. I looked at Jean Yang's class that she taught. I don't know if she was focused completely on embedded DSLs as much as my class was. She was focused on DSLs in general. Yeah, so I taught a seminar. When was that? I think that was in the fall on EDSLs. And I mean, I don't think that we're going to have an EDSL class in our department at this point. We're a pretty small department, but in seminars, I don't know if people know how research seminars work, but it's pretty much like whatever the faculty member wants to read that semester. I know, it's our secret. And that semester I wanted to read about embedded domain-specific languages. And I do think they're going to have a lot of impact, because the fact of the matter is that -02, tying back into Ali's comment of, what can we do in a general purpose compiler and those optimizations, -02, -03, those are optimizations that are being done at a 3 address code level. So LLVM level, right? Like LLVM is just typed 3 address code. So it's a very low level. You have to rediscover the loops by doing control flow analysis. And so you really have to rediscover a lot of structure at that low level. And those optimizations do a great job, and they're really important. Register allocation is important, and finding those parallel loops, even at that low level, is important, and doing loop fusion. And there's a lot of low level stuff that's really important. However, I think we're going to get more and more bang for our buck when we take advantage of the domain-specific semantics that are available. And what we need to be doing is looking at more and more ways of providing those higher-level domain-specific semantics but maybe not having to specialize per domain. And so one of the reasons I'm still so fascinated with the polyhedral model and the sparse polyhedral framework is I actually, even though those are higher level intermediate representations than like abstract syntax trees, and definitely higher level than 3 address code, they are still, in my mind, kind of an assembly language that we can map many different high-level abstractions down to. So, you know, what's a convolutional network? Well, you know, it's a polyhedral loop. and so when we come up with transformations that work well for convolutional networks and those being done in relationship to other kinds of neural networks, I think we can express those transformations at a higher level, and then kind of how can we lower a transformation down to something? What would that look like? And I think it's going to look something like the schedule mappings that you have in the polyhedral model and that you have in the sparse polyhedral framework.
All right, great. So, yeah, I mean, I think that the promise you articulated brilliantly. It's so hard to extract all of this information, and in EDSL, it's just there, and you can exploit it. So, yeah, it seems super promising, and I love the idea of this being something that you view as sort of your compilation substrate to compile the polyhedral model. That's awesome. So there's 2 interesting questions. We have 4 minutes left. We don't have a hard stop, by the way. There's the next technical talk, but I'll keep answering questions while we have questions. As long as asking questions, as long as we have them, as long as Michelle is willing to stay. So we have a question from Wenwen Wang at the University of Georgia. And Wenwen asks, how do you see the opportunities and challenges of leveraging recent ML techniques to address compiler optimization problems, e.g. loop tiling, auto-tuning, etc.? Do you think ML will beat traditional analytical approaches?
Yes, I definitely think ML is going to beat traditional analytical approaches. Because if you think about what, first of all, people have been using ML to try to solve compilation issues. I mean, like Simon's group did it way back when, like late 90s, early 2000s. So it's not a new idea. We're definitely going to be using it more. Analytical approaches are extremely difficult. And if you think about how we approach it, it's like, well, let's run some experiments and see if we can find a pattern. We as humans find a pattern, and then let's try to put that pattern into a model and then try to evaluate that model in various venues to see if it works on various architectures, on various applications. And when you've got machine learning at your disposal, then you're able to look at a lot of data and find patterns in that data, and that's just going to help you put together a model. Now, I also think it's important that we understand what those models mean. And so I think one advantage that developing models by hand has is that there's some understanding, there's some intuition as to where those things are coming from. So the work that I find really exciting is where people are trying to use the power of machine learning to come up with models, but then also trying to explain what the models that those machine learning algorithms are coming up with, and having that have some tie-in with reality. So yeah, we're going to see more and more of it.
Do you think so? It's interesting that you're basically talking about explainable models here. So I mean, I understand the intuitive appeal of these models, of wanting to know why they're doing what they're doing. But do you have, like, is there a technical reason for wanting them to be explainable, or is it just, you know, gosh, I just want to know what the hell is going on?
I think it's both. Okay, there's wanting to know what the heck is going on, and then there is the if we have some intuitive understanding of what the models are coming up with, then we as scientists and researchers and engineers really I think that'll give us more ideas of how to adjust the search space, because one of the most difficult challenges in trying to automate scheduling for large machines, automating domain decomposition, is identifying a search space. You know, what is the search space of possible schedules I'm going to consider? You know, so you know, we like to do data dependence analysis, and then that helps us constrain our search space into what's legal. But even those search spaces are of infinite size. And there's some work that doesn't even do that, right? It just tries out different possible schedules and then checks to see, well, is the schedule legal, right? And so the whole coming up with what is that search space is an art in and of itself, and it's a difficult problem. And I think that if we have some explanations coming from the models that machine learning are providing, that's going to help feed into that process of coming up with better search spaces.
Yeah, that makes a lot of sense. So yeah, I mean, I love the idea of the you know, sort of automatically giving us insights. We need that. That'd be great. But yeah, so well, I have more questions, but I'll continue with some from the audience. So John Regier at Utah says, I'd be interested to hear your thoughts on the future of auto tuners. Will they ever be mainstream? Will they use machine learning? Just leaving this open-ended. Thanks.
Okay. I think that they are, will they be mainstream? I don't know. But do I expect that they're going to get to a point where some of the scientists that I work with who are writing like big simulation codes, if we had auto tuning technology that was usable for that audience, they would definitely use it. All right. I mean, we're having an interaction this week with the HydroFrame project, which is a project I'm part of, and we're just, you know, we're trying to figure out. The scientists are like, okay, I need to understand why this code is performing the way it is, and how do I decide what kind of disks I get, and how do I decide what kind of computing power I get, and so having technology that's going to help them explore that space of possibilities and figure out, like, well, what parameters are going to result in more science being done, that's going to help them quite a bit, and they would take advantage of it. Whereas now there's a little bit of stumbling around in the dark trying to figure out how this all works. And so I don't think we can assume that all computer scientists, and definitely not all application scientists, have a rough idea of, well, where should I be looking at in this space of possible ways to run my application. And so I think auto tuners could help a lot, especially if they had some kind of IDE attached to them, if there was some kind of interaction with the user.
That's interesting. So, I mean, obviously a lot of the codes that you deal with are, you know, huge, long running, you know, that run on hundreds or thousands of nodes. I wonder, you know, I mean, I think that the culture of research in computer science in general is like, we'll run something on spec, right? And I think that the reasons for this are sort of obvious, right? It's been done before, it's easy, they're relatively fast, you can do things very quickly. What would you say, you know, that people need to be looking at especially compiler people to do things that are going to be more relevant for these gigantic, super long running codes? Like the like running something 100 times is just not feasible, right? It would take, you know, 1,000,000 years. So are there specific pieces of advice that you would have for researchers who are interested in making sure that their compiler techniques, be they traditional and analytic or using machine learning and auto tuning, would have impact in that space?
I recommend they start looking at proxy apps or mini apps. And so a while ago, I would say like 10 or 15 years ago, there was this big push in the like the government labs and the scientific computing community to somewhat deal with this problem, because we have these really large codes that at the small end are like 70,000 lines of code, like at the small end, 70,000 lines of code. And that's way too much to be testing like compiler technology that you're trying to prototype with your grad students. You can't do that. So there was this big push for, can we have these proxy applications that are like 5,000 lines or fewer of code? But 5,000 lines of code or fewer, that's quite a bit more lines of code than something in the spec benchmarks, right? And so I think that, starting there is a good way. Look at those proxy apps. They're usually made available by the Department of Energy labs, often make these proxy apps available, and you can start working with them. But I think the best way to start to get a handle on what are the problems in this area is work with people that have these large codes. And I think there's a concern of, maybe we won't be doing computer science research, and it may slow things down a bit because you're working with real problems and you're working with real codes. But I think that it'll help identify what are the real problems that these folks are running into, and how are some of our technologies that are really cool and have been around for, in some case, decades, could they be brought to bear in this, and they just need somebody to like help do that technology transfer for them? And are there some interesting research problems in doing that technology transfer so that other people can use it? So that's what I would recommend.
All right, great. Muted, sorry.
Yes.
Somehow I muted myself.
I was going to say, have I lost my connection? Okay.
So let's see. So we'll stick with right now. There's a couple non-technical questions in the thread. We'll wrap up with a technical question for now and then address the non-technical ones. So the question is from Kishanthan Sundaraja from Purdue, who asks, can you comment on using polyhedral techniques for data flow programming models? What are some of the interesting research ideas in this direction? And I'm not sure if the question is about things like TensorFlow, which obviously is data flow, but or more general.
Yeah. Well, so when we do have these graph-like representations, data flow representations of a computations that's being going on, imagine that each node in that graph is essentially a polyhedron. And so if you think of these graphs as being a way of, in a non-polyhedral way, connecting up the polyhedrons, and then now we have this whole search space of, all right, well, how do we optimize, how do we schedule between the polyhedrons? And there's definitely a lot of people looking at some of that work. So some of our work is the loop chaining work. Is, can we have abstractions that are not just at the loop level, but of many different loops that share data, because that pattern often happens in scientific codes. And so, yeah, I think there is a lot of promise of bringing the polyhedral model to bear. And I mean, we use that term polyhedral model a lot, but I think the key piece of the polyhedral model that I see as getting traction is it's a more structured way of doing metaprogramming. Okay, so it's a very structured way of representing your computation and then orthogonally scheduling and coming up with the data mapping for it. And so I absolutely think that, and yet I still think of the polyhedral model as an assembly code language in the metaprogramming world, if you will. And so we just need to figure out how to raise that level of abstraction. And I think these data flow graphs that then have nodes that are polyhedrons in them are one of those ways to raise that level of abstraction. And then we've got a whole bunch of room for solving those problems. How do we schedule those? Great.
All right, so off to the some questions about education and other things. So
okay.
John Wickerson at Imperial says, you teach several courses related to your research on compilers and PL. Have you ever found teaching students directly helpful to your research? E.g., Has explaining something in a lecture ever led to a new research idea?
Absolutely. Absolutely. I mean, that's one of the reasons I love teaching, is because of the fact that, you know, when I'm explaining things to students, they lead to, they ask me questions I didn't think of, and that leads to research ideas. And so I'm trying to come up with a couple of concrete examples. So one very concrete example is I've been teaching compilers and grad compilers and like systems programming level, like assembly language programming, all the different levels of abstraction for many years. And this past spring, the long semester that seemed to take forever, but it was great semester because I taught grad PL for the first time ever. So I taught Norman Ramsey's graduate programming languages course, and it was fantastic. Like, I learned operational semantics. I mean, I'm pretty sure I learned it back in grad school, but like I really learned it because I had to teach it. And so some of the ideas that I'm getting out of there are, I've gotten some ideas of how to apply some of that more structured induction proof technique to some of the things that we're doing in the Sparse Polyhedral framework. And some of the questions that students have asked, because these were all students that really came from an imperative programming background. So some of the students they've asked, questions they asked have helped me think of research ideas. But another, like one of my toy projects right now has been also come from interactions with students and from interactions with other people at PLDI. So in 2016, I was at PLDI, I think this was Santa Barbara, and where we actually got to go in person. And I was leading a session, and there were 2 polyhedral papers, and then there was this paper about parsing with derivatives. And I'm like, what is this? And why is it in my polyhedral compilers section? So I read the paper ahead of time so that I'd have questions. And then Michael Adams gave the talk, you know, one of Matt Might's students gave the talk. And I was like, this is kind of cool. This whole parsing with the derivatives thing is kind of cool. So I've been playing around with it for, well, ever since then, since 2016, so 4 years. And then I taught CS3 in my department for a couple semesters. And we were developing a new class. So we're getting lots of feedback from the students of what were some problems you ran into. And so it's CS3. And one of those things that that really resonated with the students when we talked about this in class is we're spending most of our time writing the code that parses the input.
So quick interjection. Can you tell the audience what CS3 is broadly as a class?
So CS3 is kind of like it's programming in Java, data structures, different algorithms, right? And so they've taken, in our department, they take 2 classes, CS1 and CS2 are in Python. So this is transitioning to another language, understanding some of the similarities between these different languages, and then different data structures and interfaces. So they're doing a programming assignment every week and learning about trees and writing programs about trees, et cetera. But their comment was, we're spending most of our time doing the parsing. And so that made me really think, like, wow, you know, it's true with beginning programmers, the current parsing tools that we have are too complicated for beginning programmers to use. And so we have them do this ad hoc parsing of input. And maybe we're losing some really good computer scientists because they're like, I have to, you know, spend all my time just making sure that I'm parsing the input that the professor's providing me. They're not spending their time thinking about the trees. Anyway, so now I'm on this big kick of like, we need to change this, and we need to provide parsing tools that a beginning programmer can use. And hey, we should be able to do this because we have these beautiful abstractions of regular expressions and context-free grammars. So why don't we just give the beginning programmer, like, here's the regular expressions and the context-free grammars that you need for this input. Like, just use it and have a library that just parses it in for them, and then they spend their time on the data structures. So yeah, I definitely get ideas from students.
Nice.
That's
Yeah,
a long answer to a very short question.
That's a well. What's the meaning of life, Michelle? It's a very short question. Okay, so so Ali has a question. If there's time, sure, I would love to hear from you about SIGPlan Cares. I don't have a specific question about it. Would love to know what your involvement is and generally how well you think it's working as an initiative. And he adds, perhaps you could plug the #Cares channel in our workspace too. So consider it plugged.
Yes. So SIGPlan Cares is a group that Catherine McKinley, my understanding is Catherine McKinley has spent a lot of time and effort trying to get SIGPlan Cares going. It is a group of people. We are here, and I am part of that group. I was pulled in by Catherine and David Walker. Catherine McKinley and David Walker. We are here if people in the community need support. You know, maybe you're not feeling like you're being included in a conference or you're having some issues. It's interesting because one of the most frequent questions that we get in SIGPlan Cares is, do we really need this? Unfortunately, we do. As a community, we really do need a way to support people. I know that when I was a grad student, just starting to go to conferences, I was actually quite fortunate because at that time, I was already married, but I had like fellow female students that would wear fake wedding rings when they went to conferences. Okay, so, and we won't get into why they did that, but I imagine people can come up with reasons why people might do that. So we do need it. If you want other examples to try to understand this problem better, Catherine McKinley has a wonderful blog post about the community that you experience is not the one that we do. And so I think we need to realize that there are all different kinds of people that don't necessarily feel welcome in programming languages and in research and in computer science in general, and have unfortunate things happen to them in these settings. And so we as a committee are here to support them and help them. We don't do reporting for them. We're not police officers, but what we do is we are here for the people, for anybody who's having any kind of trouble. We let them know what resources are available and support them through any kind of process, whether they just need to process it verbally with another human being, or they want to report it, or anything like that. And the biggest reaction we've had, especially from junior folks, actually, which means to me that we are making a difference, is people are just glad we're here, because it's a signal that SIGPlan is aware that there is an ongoing issue in computer science and in programming languages, and that we want to help support people as the community evolves and continuously improves.
Yeah, thanks so much for doing this. Not just the AMA, but that work. I think it's super important. So let's make this the final question. Actually we have two questions. So good. I think we can just get them in before 5:40. So the first one isn't really about research or your research in particular, but it's an interesting question. So it's from Shreyas Kandakar from University of Arizona. And the question is, colleges have seen a downward trend in the number of tenured professors, I assume tenure track, counterbalanced by an increasing number of adjunct professors. This means a lesser number of research input and thus lesser output, although research output has yet to catch up with this trend. What do you think is the future of research due to this? And do you think COVID has accelerated this issue?
Interesting. So Shreyas is one of my undergrad students. And so this is an example of students coming up with questions that are hard to answer. I actually think that the reason why we've had, it's not adjunct faculty, but more teaching faculty in computer science is mostly because of a lack of supply of there just aren't enough people that are tenure track, that want to be tenure track faculty in computer science, right? I just don't think, I mean, I think Emery is shaking his head yes. Both Emery and I at different institutions, and I've been at 2 different institutions, you know, we've been on this side of trying to hire tenure track faculty for many, many years now. Dare I say, like more than a decade. There are a lot of good people out there, but there's a lot of opportunity in industry. And that's fantastic. And I'm thrilled that my PhD students coming right out make more money than I do. But there's a lot of opportunity in industry. And so the reason why we've had, in my opinion, in our field, that we've had more and more teaching faculty is because of an issue with supply. We don't have enough tenure track faculty. Now, one of the great things about teaching faculty is they're focused almost solely on teaching. So as much as I love teaching, and I do, and I spend a lot of time on it, I spend a lot of time on research and advising my research students and taking them through the process and teaching them how to do research. That doesn't leave a lot of time to figure out how do you do active learning for very large classes, which is in computer science, that's what we have right now, is we have very large classes. Now, I have spent some time learning how to do active learning in very large classes, but I don't have as much time to focus on that as teaching faculty do. So I think teaching faculty have really become the backbone of computer science departments in the age where our undergraduate enrollments are still exploding and still going up. And we want people to learn about computer science and how they can use computers to solve problems. And so this is a good thing. We want it to keep going. But to keep doing that, we're going to keep hiring tenure track faculty. We're going to keep hiring teaching faculty, and it's going to keep going. It may have a pause for a year. It may slow down for a year, but because of COVID, but it will keep going.
Yeah, I mean, I think, you know, like you said, you saw me nodding my head. I mean, I think that the demand for computer science has just grown so fast. It's hard already to hire faculty, tenure track faculty, and hiring enough to keep up is just not possible.
Yeah, and to be fair, it's just as hard to hire teaching faculty.
Yeah, it's also hard to hire.
It's hard. It's just a slightly different population. It's like a population of people that they thought research was okay when they were in grad school, but they would rather focus on the teaching. And so we need to hire from all the populations we can.
Absolutely. Couldn't agree more. All right, let's make this the last question. I think this is a lovely question to close with. So this is from Paul Kelly at Imperial. Our PhD students are often studious and somewhat introverted and not always confident. Do you have any experience to share on how to build their confidence and ambition to develop into research leaders, like yourself?
Did he actually say that, or are you just putting it in there for him?
I'm sure that's what he meant.
I'm sure that's what he meant. Wow, Paul, that's a tough question. I think that the confidence issue is something that we all deal with, and especially in research, because we're trying to solve things that people haven't solved before. And so, we're going to go down blind alleys, and we're going to hit brick walls, and we're going to make mistakes, and we're going to get rejection, because there's a lot of rejection in research. Like, our grant proposals get rejected, our papers get rejected, and there's just a lot of rejection. So so how do I help students get through that? Well, part of it is letting them know, giving them a heads up that there is a lot of rejection in research, and there's a lot of failure in research. And really the key, in my mind, the key personality trait, or the key, not personality trait, but the key skill you need to build to be a researcher is your tenacity. So, you know, really keep trying to work on problems, keep trying to make progress, but not tenacity so much that you only take one approach to a problem, right? So you also have to have flexibility. So you have to be willing to, you know, hey, if I'm trying this approach and it's not working, it's not working, consider other approaches as well. And build a community for yourself. Because I think this also helps as well. If it's hard to do research within a silo. In fact, I would argue it's almost impossible. Every time we talk about an idea in a research meeting, we learn new holes in the idea, and then we go fill them and we figure out how to fix things. And so that collaboration within your own research group is crucial. And finding those external collaborators that will work with you are crucial. So ask questions and find your support system to help out. And the other key thing that I would like to end with is that there's a lot of really nice people in this community. I know I'm on CARES and I talked about how there's some issues in the community, but overall, there's really fantastic people in this community. Emery, for example, we've always talked a lot, and he's been very supportive of me forever. But another great thing about this AMA session, I was kind of blown away because, like, well, these people have been my mentors. Most of these people, like Catherine McKinley has been my mentor for decades. Ann Rogers. Bjarne Strastrup, in '97, I did an internship at AT&T Labs, and my office was right next to his. And like the last day of my internship, I took my C++, my copy of my free copy of the C++ book. I took it in and asked him to like sign it for me, and he's super nice. And I've been carpooling with Ravi Sethi, one of the authors of the compiler book, for the past 5 years, and interacting with him. And it's just like, there's some really great people in this community that are willing to be supportive. And even if they're famous, usually, if they're pretty famous, they're also pretty nice too. So ask questions and realize that all of us in this community, we're humans too, and most of us are super nice humans.
Thankfully, I think that is mostly true.
Yes.
So thanks, Michelle. This was wonderful. I really enjoyed it. And I hope everybody out there enjoyed it too. And gosh, I look forward to doing it again, and maybe even seeing you sometime in person instead of staring at a camera on my laptop.
Thank you, Emery.
All right, bye-bye.